Hey, this is Presh Towalkar. You may have heard that Harvard is teaching remedial math. Before I explain whether they actually are teaching remedial math, I want to go into the history of where this idea came about. In September of 2024, the student newspaper, the Harvard Crimson, ran an article, Harvard launches new intro math course to address pandemic learning loss. They said the course would be aimed at rectifying a lack of foundational algebra skills, and the course would be titled Math MA5. The idea that students at Harvard would lack foundational algebra skills was quickly picked up by critics. Very recently, this led to a New York Post opinion piece with the title, Harvard University, the Ivy League, Teaching Remedial Math. The article points out that during the pandemic, Harvard scrapped the standardized testing requirement, which would allow students who presumably did not have the foundational skills to be admitted into Harvard. These ideas have a way of percolating to the top, and here is what President Trump said recently.
Why do you not want the best and brightest from around the world to
I do.
come to Harvard?
I do, but a lot of the people need remedial math. Did you see that? Where the students can't add 2 and 2 and they go to Harvard. They want remedial math, and they're going to teach remedial math at Harvard. Now, wait a minute. So why would they get in? How can somebody that can't add or has very basic skills, how do they get into Harvard? Why are they there?
In response to the president's claim, the Associated Press did a little bit of fact-checking. They ran an article, Fact Focus. Trump's claims about remedial math at Harvard don't add up. They reach out to Harvard specifically, and the response is that Harvard does not offer any so-called remedial math classes. The new course, Math MA5, is a college-level calculus class. It has the exact same homework, exams, as grading structures as previous courses, and the only difference is that the new class will meet 5 days a week. To give further evidence of their point, Harvard has released sample exam questions from this so-called remedial math course. So it is now up to you to judge. Could you pass Harvard's so-called remedial math class? Let's start out with problem 1. An epidemic is spreading through an island, and the number of cases is growing exponentially. At the start of the epidemic, there were 10 cases, and the total number of cases triples every 14 days. Part A, write a formula for E of t, the total number of cases t days after the start of the epidemic. So we first know that the number is going to grow exponentially. So the function E of t will have the form a constant c times a constant b raised to the power of t. It remains to solve for c and b. So we know that at the start, there were 10 cases. So when the time is 0, we know that there will be 10 cases. So E of 0 will be equal to c times b to the power of 0, which equals 10. B to the power of 0 will be equal to 1, which means that c is equal to 10. It only remains to solve for b. What else do we know? We know that the total number of cases triples every 14 days. So we know that 14 days later, which will be E of 14, the number of cases will be 30, because that's triple of 10. So we can substitute in that this is equal to 10 times b to the power of 14. We divide both sides of the equation by 10, and then we take 1 over 14 to both sides, so that we get b is equal to 3 to the power of 1 over 14. And therefore, we have that E of t is equal to 10 multiplied by 3 to the power of 1 to the 14th, and this is all raised to the power of t. This can also be simplified where we bring the t as part of the exponent, so E of t is equal to 10 times 3 to the power of t over 14. So let's take this answer to part A, we'll move it over here, and now let's solve part B. What is the percent increase in the total number of cases between days 5 and 19? Explain how you know in 1 to 2 sentences. We know that the number of cases triples every 14 days. So between days 5 and 19, we know the number of cases will triple. So if the number of cases will triple between days 5 and 19, we have to figure out how this is a percentage increase. Doubling is a 100% increase, so tripling will be a 200% increase. So the percent increase will be 200%. Now let's move on to part C. What is the daily percent increase in the total number of cases? You may leave your answer in unsimplified form. The formula for daily percent increases in the total number of cases will be the change in the number of cases divided by the number of cases. So we have E of t plus 1 minus E of t, and this is all over E of t. We just substitute into the formula that we have for E of t. Notice what's in the denominator can be divided through. So this will simplify tremendously. The very first term in the numerator will just be 3 raised to the power of 1 over 14. And then E of t divided by E of t, this will work out to be 1. So the daily percent increase in the total number of cases will be 3 to the power of 1 over 14 minus 1. We want this to be a percent, so we will multiply this by 100%, and that is the correct answer. Now let's move on to question 2. Marta is watching a bacteria sample exponentially decrease in size. At 3 p.m., there are 2,000 micrograms of bacteria, and the sample is decreasing in size at a rate of 500 micrograms per hour. Part A. How large is the sample of bacteria when the sample is decreasing at a rate of 100 micrograms per hour? So we know that the sample is exponentially decreasing. That means the rate of change is proportional to the amount that's already there. This can be expressed in calculus form that n prime of t is equal to some constant lambda times n of t. Now let's use the given information. We know that initially at 3 p.m. there are 2,000 micrograms. We also know that the sample is decreasing at the rate of 500 micrograms per hour. So initially, we must have n prime of 0 equal to minus 500, and we also have n of 0 is equal to 2,000. Substituting into the general form, we get the equation minus 500 is equal to lambda times 2,000, which means that lambda is equal to minus 0.25. We need to know how large the sample of bacteria is when the sample is decreasing at a rate of 100 micrograms per hour. So we substitute into this equation, and we need to see what happens when n prime of t is equal to minus 100. In this case, we divide both sides by minus 0.25, and so n of t is equal to 400. So the sample size is 400 micrograms. Now let's go to part B. Which of the following functions could describe the amount of bacteria in micrograms at time t hours after 3 p.m.? Now we know initially there are 2,000, and we know that lambda is equal to minus 0.25. So the only option that will work here is option 5, which is 2,000 times e to the power of minus 0.25t. Now let's go to part C. Marta is working on understanding the derivative of an exponential decay function and has come up with the following graphs of f of x is equal to 1/2 to the power of x and f prime of x. In the graph below, f of x is a solid curve and f prime of x is the dashed curve. Marta's graph of f prime of x is incorrect. Explain why in 1 to 2 sentences, then sketch a possible graph of f prime of x on the axes above. Now, if we have a function that represents exponential decay, it's obvious that the function f of x is decreasing everywhere. A function that is decreasing everywhere will have a derivative that's negative, so f prime of x has to be less than 0. So Marta's graph shows f prime of x as always greater than 0, so it must be incorrect. We could actually do the mirror image of the graph she has sketched, and that is one possible way that we could graph f prime of x. Question 3. Let f of x be equal to 1 divided by 3 to the power of x minus 9 times 1 divided by 3 to the power of x plus 3. Part A. Find all values of x on negative infinity to infinity, where f of x is not continuous, and classify each point of discontinuity as a removable discontinuity, jump discontinuity, or vertical asymptote by computing appropriate limits. So to solve this question, we need to look for places where either of the denominators will be equal to 0. So let's start out with the second fraction. This denominator is 3 to the power of x plus 3. Now 3 to the power of x is always greater than 0, so 3 to the power of x plus 3 will never be equal to 0. We will never have any sort of discontinuity because of the input to this second fraction. But what about 3 to the power of x minus 9? We could have this equal to 0. In fact, we would have a solution when x is equal to 2 because 3 squared is equal to 9 and 9 minus 9 is equal to 0. So we know that at x is equal to 2, we will have a discontinuity. But what kind is it? Let's analyze the behavior around x is equal to 2. If we consider the fraction 3 to the power of x minus 9 around x is equal to 2, we know that the denominator is going to be going towards 0, and the numerator is going to be 1. So we're going to have a form like 1 over 0. Let's see what happens when we approach from numbers that are slightly smaller than 2. In this case, 3 to the power of 1.99 minus 9, this will end up being a number that's less than 0 because we know that 3 squared will be equal to 9. So if we take the limit going from the left side for numbers that are slightly smaller, we know that this denominator is going to be a negative number. So we're going to have 1 over a very small negative number. So this is going to be a limit that goes to negative infinity. If we were looking at the other side, we're going to have slightly positive small denominators. So the limit from the right side will be positive infinity. So we can see here that this type of discontinuity will be a vertical asymptote at x is equal to 2. Now let's go to part B. Find the limit as x goes to infinity of f of x. So we'll take this limit and we'll consider what happens to each of the denominators. 3 to the power of x will go to infinity. So this first fraction will be 1 divided by some very large number. This will go to infinity. Then we have the second fraction. Again, 3 to the power of x is going to go to positive infinity. We add 3, this will also be positive infinity. So this entire denominator is going to go to positive infinity. So we have 1 over positive infinity times 1 over positive infinity. And this is going to be 1 over infinity is going to go to 0. So the limit as x goes to infinity of this will be equal to 0. Part Z. Find the limit as x goes to negative infinity of f of x. So we'll analyze each of the denominators again. In this case, 3 to the power of x is going to go towards 0 as x goes to negative infinity. And the same will be true in the other fraction. So the first fraction is going to go to 1 over minus 9. The second fraction is going to go to 1 over 3. The product of these will be minus 1 over 27. And that's the answer. Question 4. Consider the function f of x is equal to x to the power of 3 minus 6x squared plus 18. A. Identify the critical points of f of x. A critical point is when f prime of x is either equal to 0 or is undefined. Now f of x is a polynomial function, so it's never going to have an undefined derivative. So we just look for cases where f prime of x is equal to 0. F prime of x is equal to 3x squared minus 12x. We set this equal to 0. We can divide both sides of the equation by 3, and then we can factor x. So x times x minus 4 is equal to 0. This has solutions that x is equal to 0 or 4. And those are the critical points. Part B. On what interval or intervals is f increasing or decreasing? Please show your work fully. Let's visualize the answer with a number line. We know that at x is equal to 0, f prime of x is equal to 0. We also know that at x is equal to 4, f prime of x is equal to 0. So what happens to the left of 0, in between 0 and 4, or greater than 4? all we need to do is test one value. So let's consider x is equal to minus 1. We can evaluate that f prime of negative 1 is equal to 15, which is greater than 0. So we know everything to the left of x is equal to 0 will have the same sign. We know that the sign can't change because x is equal to 0 is the first critical point. So we know that to the left of x is equal to 0, f prime of x is positive. Then what happens in between 0 and 4? We can take a sample value like f prime of 1. In this case, it's equal to minus 9, and that will be negative. So between 0 and 4, the first derivative will be negative. Let's look at a value greater than 4. We can evaluate f prime of 5. This will be equal to 15, which is greater than 0, and that is a positive value. When the derivative is positive, we know that f is increasing. So that's true when x is less than 0 or x is greater than 4. And in between 0 and 4, the derivative is negative, so f is decreasing. And that's the complete answer. Now we'll take this information and we will need it to solve the next part. C. Classify the critical points as local maxima or local minima, given your work in the previous parts of this problem. So notice that right at x is equal to 0, the derivative is changing from positive to negative, so the function is changing from increasing to decreasing. So if a function is first increasing, and then it starts decreasing, that will of course be a local maximum. Now when we have x is equal to 4, this is a point where the function goes from decreasing to finally starting to increase. So at x is equal to 4, the function will be a local minimum. Now let's go to part D of the question. Does f of x have any global minima or maxima on the interval minus 15 to minus 3 inclusive of both endpoints? If so, where? At what x value? Support your answer in 1 to 2 sentences. Now we know that the function will be defined on the entire closed interval. F of x is also continuous and increasing from minus 15 to minus 3. So we know at the very beginning that must be the smallest value. So x is equal to minus 15 will be a global minimum. And then it just keeps increasing all the way to the endpoint. So we know that x is equal to minus 3 is a global maximum. Part E. Does f of x have any global maxima or minima on the interval minus infinity to infinity? If so, at what x value? And support your answer in 1 to 2 sentences. F of x is a polynomial, and we know that its highest term is x to the power of 3. So this term will dominate when we take x goes to infinity or negative infinity. So if we take a look at the limit as x goes to infinity, we know that some positive term that's cubed is just going to get bigger and bigger, so f of x is going to tend to infinity. If instead we take a look at what happens when we go to negative infinity, a negative term that will be cubed will still be a negative term, so f of x is going to go to minus infinity. So we know there cannot be any global maxima or minima because the function at the endpoints is just going to keep increasing or decreasing. So there is no global maxima or minima. Question 5. Ming Lee is publishing a poetry book and is trying to figure out the page size. Each page consists of a rectangular text body where the text is and margins on each side. The top, bottom, and outer margins are all 1 inch. And the inner margin by the spine of the book, called the gutter, is 2 inches, so there's room for the binding. The area of the text body needs to be 24 square inches. Here is a diagram of the page. The outside rectangle is the page, and the inner shaded rectangle is the text body. We have drawn arrows spanning the margins for you and defined 2 variables to get you started. Let L and W be the length and width of the text body in inches. He wants to minimize the total area of the page to save on cost. What should the dimensions of the page, length and width, B in order to achieve this. For full credit on this problem, please show your work fully. There is more space on the next page. And make sure to highlight the following. State your goal. Given the diagram, clearly define your variables and label any constants. Communicate your thought process one step at a time. Write down how you find and classify the global extrema, justifying that it is a global extrema and not just a local max min. Be sure to answer the original question asking for the dimensions of the page. So let's start out with the given information. We know that 3 of the margins are 1 inch each. So we have a 1 inch margin at the top, on the right side, and at the bottom. The gutter will be 2 inches, so this will be 2. We now need to look at the goal. We know that he wants to minimize the total area of the page. So we have the dimensions of L and W, but we need the dimensions of the entire page. So we add in the appropriate margins. So one of the dimensions will be equal to W plus 3, and the other dimension will be equal to L plus 2. We want to minimize the total area, which will be the product of these dimensions. But we know the minimization is subject to some constraints. The area of the text body needs to be 24 square inches. The text body will be L times W, so that needs to be equal to 24. We also want the dimensions to be positive numbers so that we have some text body. We need L and W to be greater than 0. So now let's just focus on the mathematics and these formulas. Let's get started by expanding W plus 3 times L plus 2. This is equal to L times W plus 3L plus 2W plus 6. But we know that L times W is equal to 24. From the equation L times W is equal to 24, we can solve that L is equal to 24 over W. So we can substitute in for L. So this equation will become 24 plus 3 times 24 over W plus 2W plus 6. And this will simplify to be 30 plus 2W plus 72 over W. And we can set this equal to be a function f of w. So at this point, we want to minimize this function. So let's calculate its derivative. F prime of w is equal to 2 minus 72 over w squared. Now, where are the critical points of the derivative? We will have one critical point where w is equal to 0, but we know that both L and w need to be greater than 0, so we can forget this point. We know it's not applicable to this practical problem. So let's see where the derivative is equal to 0. We can solve this equation, and we will get that w squared is equal to 36. We can't have a negative value of w, so we only take the positive root that w is equal to 6. Now we need to check that this is a minimum, and we can take the second derivative and see that it is always positive, which means that this is in fact a minimum. So we now need to go back to the original problem. We have solved that w is equal to 6 will give us a minimum, but we need to solve for the dimensions. So we have w is equal to 6. We know that L is equal to 24 over w, which means that L is equal to 4. But what are the original dimensions? The dimensions are w plus 3 and L plus 2. So we need to substitute in, and we get that the dimensions are equal to 9 inches and 6 inches. And this will have a total area which is equal to 54 inches squared. And that's the answer. So now let's go to question 6. In this problem, you'll use a tangent line approximation to approximate the square root of 17. Part A, what function will you use to approximate the square root of 17? It would be very natural to take the square root function. In particular, take the principal square root of x. Part B, sketch the graph of the function you chose. Make the graph large because you will add to it later. So here we have x and y axes, and we will sketch the graph that f of x is equal to the square root of x. Part C, approximate the square root of 17 using a tangent line approximation. So we first need to think about a square root that we know that's close to the square root of 17. So let's think about the square root of 16, which is equal to 4. So when x is equal to 16, we know that the square root of x is equal to 4. So we have the point 16, 4, which is on this graph, y is equal to the square root of x. We want to know what the square root of 17 is. So we want to know the y value when x is equal to 17. So how can we do that with a tangent line approximation? Let's sketch the tangent line when x is equal to 16. We can then consider what happens on this line when x is equal to 17 and compute its y value. So the y value on this line will be our tangent line approximation to the square root of 17. So how can we solve for that? So we will first calculate the slope of this line, which is exactly equal to the derivative when x is equal to 16. So let's say that the square root of x is equal to f of x. F prime of x will be equal to 1 divided by 2 times the square root of x. If we evaluate this at x is equal to 16, we get that f prime of 16 is equal to 1 divided by 2 times the square root of 16, which is equal to 1 over 8. So we know that's the slope of the tangent line. So now let's sketch a handy little triangle here. When we go from x is equal to 16 to x is equal to 17, we have a change in x that's equal to 1. But how much is the change in y? That will exactly be equal to the slope of this line times the change in x. The change in x is equal to 1, so it is exactly equal to 1 over 8 times 1, so the change in y is equal to 1 over 8. So when x increases to the right by 1, we know the y value is going to increase by 1 over 8. So we can solve that y will be equal to 4 plus 1 over 8, and this simplifies to be 33 over 8. And that's our approximation to the square root of 17. Part D. Is your approximation an upper bound or a lower bound for the actual value of square root of 17? Explain in 1 to 2 sentences using your picture in B to illustrate. Now in this picture, we can obviously see that the tangent line is larger than the curve, so this is going to be an upper bound. The tangent line will be above a concave down function like f of x is equal to the square root of x, so this value will be larger than the actual value of the square root of 17. Question 7. In each part, either sketch an example of a function f with the given properties, or say that no such function exists and explain why in 1 to 2 sentences. Make sure any sketches clearly meet the given conditions. Part A. F is defined on the closed interval from -2 to 2 and is no global maximum or global minimum. So we need to sketch a graph. Let's do it on the following axes. So one way we could do this is we could just have a straight line where the endpoints are open. So in this case, we know there's no maximum or minimum because you could keep getting closer and closer to a value, but it won't be an actual maximum or minimum. Part B. F is defined on -2 to 2, the closed interval, has a global maximum at x is equal to 0, and has no global minimum. So let's put a graph where we have a V shape where we know the maximum is at x is equal to 0, and we don't want any other global minimum. So let's just put an open endpoint on the left, and we can put an open endpoint on the right, just as one possible example. Part C. F is continuous on -infinity to infinity, and we have the limit as x goes to -1 from the right of f of x is not equal to the limit as x goes to -1 from the left of f of x. Well, we have a problem in this question. If f is continuous, then we will always have the left and right hand side limits be equal to each other, but they're telling us that these two limits are not equal to each other. This is not possible. There's no way you can have a function that's continuous, but you have this condition where the left and right limits are not equal to each other. There is no way that we can graph this. No such function exists. Part D. F has the domain of the open interval from -2 to 2, is continuous on its domain, and differentiable everywhere on its domain except at x is equal to 1. So here's one possible graph. At x is equal to 1, the function is continuous, but it is not differentiable because we have a corner point, and otherwise we just have line segments, so we know that it's going to be continuous everywhere and differentiable everywhere, except for the point x is equal to 1. We know that the function is not differentiable. So that's one way you could do this. And this concludes the sample test for our remedial math course. I would be very curious how politicians in America do, and I'm curious how well you scored on this test. Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.